Hi and welcome to Chem with Dr. M. In this video we're going to look at calculations related to mass spectrometry, where we're going to calculate the average relative atomic mass of elements, calculate the abundance of different isotopes of elements, and use the equation Ke equals 1/2 mv squared in mass spectrometry calculations. I've discussed the theory behind how a mass spectrometer works in an earlier video, so please look out for that one. And remember, if you enjoyed this video and find it useful, please like and subscribe. This is absolutely free for you to do and will help more than you realise, as it will allow me to make more content like this in the future. Now I'm going to go quite quickly through our first example, as most of you will be very familiar with this from GCSE and there's really no difference here at A-level. We've been given a mass spectrum of copper and we can see that there are two peaks. In this case that shows that there are two isotopes, one with an MZ value of 63 and one with an MZ value of 65. We want to calculate the average relative atomic mass of all of these isotopes by taking the abundance of each isotope into account as well. Now here we can see that there is more of the 63 isotope than there is of the 65 isotope, and we're going to get a weighted average of the two. Now the calculation to work this out is given by the abundance of each isotope multiplied by their mass. Add all of those together for each isotope and divide by the total abundance. Now the total abundance is often a percentage, so the total is often 100%, but it doesn't have to be, and that's the case in this example here, which is why I've chosen this one to do. So if we substitute that calculation for numbers, we can say the average relative atomic mass is 120.8 multiplied by 63 plus 54.0 times 65 divided by the total abundance, which is 120.8 plus 54.0. If we put all of that into our calculator, we get 63.6. This is our final answer, and we always give relative atomic masses or relative formula masses to one decimal place, even if that decimal place is 0.0. That's because they're all quoted to one decimal place in the periodic table. Now what we can also do here is we can check this versus our data booklet, because we'll always have that in an exam. We can see that our answer is 63.6 and copper on the periodic table is 63.5. So we're assuming that we're in the right area here, and we're thinking that our calculation is probably correct. Now those were the easiest type of mass spec calculations. They might also ask you to do something very similar but the other way around. You might be given the masses of different isotopes and the average relative atomic mass, but you might be asked to work out the abundance of each isotope. Now this involves using algebra, and I know that students can find this tricky, especially students who don't take A-level maths or who weren't confident with algebra at GCSE. Please do rest assured that the algebra I'm going to do here is no more advanced than GCSE, and once you know how to do these, they are almost all the same. Now I'm going to talk you stepwise through this, and I'm going to do the algebra step by step. Some of you may feel confident at rearranging the equation, and you might combine some of these steps and do them in one rather than in each individual step like I'm going to do, which is also absolutely fine. I'm just really spelling it out here for students who aren't confident. So what does it tell us in the question? Well, it tells us there are two isotopes of copper, copper 63 and copper 65, and it tells us that the average relative atomic mass of the sample is 63.6. It wants us to use this information to calculate the relative abundances of those two isotopes. So what we have to do is use algebra, and we have to say, first of all, let the abundance of one of them, I'm going to go for the smaller one, copper 63, be the value y. Therefore, because there's only two isotopes here and the abundance has to add up to 100%, I'm going to say, therefore, the abundance of 65 copper must be 100 minus y, 100% minus the percentage due to copper 63. So I can put this into the calculation that we had on the previous slide. The average relative atomic mass is given by the abundance times the mass of each isotope added together, divided by the total abundance. So let's substitute now using some numbers and using y's. So our average relative atomic mass is 63.6. That equals y times 63 plus 100 minus y times 65, over the total abundance, which is a percentage, which is 100%. Now I have to be confident at multiplying out those brackets. Again, I'm doing this step by step, but you might be able to do this quicker and combine multiple steps. So if I now multiply out those brackets, I end up with 63.6 equals 63y plus 6,500 minus 65y, all divided by 100 again. I can then get rid of the 100 off the bottom of my equation by multiplying both sides by 100. So I end up with 63.6 multiplied by 100 is 63y plus 6,500 minus 65y. Again, going stepwise, that gives me 6,360 equals 63y plus 6,500 minus 65y. If I rearrange that, because I don't want any negative numbers here, because I can't end up with a negative percentage, I end up with 65y minus 63y equals 6,500 minus 6,360. That leaves me with 2y equals 140, and therefore y equals 70. So that means it's 70% for 63 copper and 100 minus 70, which is 30% for 65 copper. Going back to what we said at the very start, letting the abundance of 63 copper be y and the abundance of 65 copper being 100 minus y. If you wanted to, you could check this again by plugging those numbers into your average relative atomic mass calculation, just to check that that does give you 63.6. So now it's time for an exam style question. This one is a little bit tricky initially, but once you've set up your initial equation, the technique is exactly the same what I did on the previous slide. Try and have a go on your own, but if you're stuck, you could possibly just watch the initial part of the answer to help you set up your equation and then try it on your own. Or if you're really stuck, watch it again on your own before you have a go of some exam questions that you've got from your teachers. Okay, so press pause now, have a go on your own, and then I'll go through the answer. Okay, so hopefully you've had a go on your own. This is a bit more tricky because this time there are 3 isotopes of chromium. There's chromium 50, chromium 52 and chromium 53. Again, it tells us the relative atomic mass overall is 52.1, but it tells us this time that 86.1% is due to the 52 chromium isotope. So we have to just set this up initially slightly differently to what we did before. But again, we want to know the relative abundances of the 2 other isotopes. So again, we're just looking for the abundances of 2. So it is very similar to what we did before. Now, the bit that's a little bit different is we initially have to say that the percentage of chromium 50 and chromium 53 added together must be 100 minus the 86.1% that was due to the chromium 52. So that leaves us with 13.9% left over, which must be the chromium 50 and the chromium 53 added together. Now that we know that, we can proceed exactly in the same way as we did before, by saying, let the abundance of chromium 53 be y, and therefore the abundance of chromium 50 must be 13.9 minus y. So if we put that into our relative atomic mass equation, we can say 13.9 minus y times 50 plus 86.1 times 52 plus y times 53 is 52.1. Those are all divided by 100. We can multiply out those brackets just like we did before, and we end up with 695 minus 50y plus 4477.2 plus 53y over 100 is 52.1. Again, rearranging, we end up with 695 minus 50y plus 4477.2 plus 53y is 52.1 times 100. Multiplying that out again and rearranging, we get 5172.2 plus 53y minus 50y is 5210. Rearranging gives us 53y minus 50y equals 5210 minus 5172.2. That gives us 3y equals 37.8, and therefore y must equal 12.6. And therefore 12.6% is for 53 CR, and 13.9 minus that 12.6 is 1.3 for the chromium 50. Again, you can check all of that by plugging the 3 abundances and the 3 relative atomic masses of each of the 3 isotopes into the overall equation and checking that it equals 52.1. So now we're on to time of flight mass spectrometry calculations, which are the most tricky type in this topic. Again, once you've got the hang of these, they're actually okay and they follow a very, very similar pattern. You do get the odd unusual one on exam, but by and large they're okay. There are a few places where students commonly go wrong on these, and this is what I'm going to point out as we go along. So in this example, we've got compound Y, which is ionised by electron impact ionisation. Now, if you've seen my earlier video in this series, you'll know that the equation for electron impact ionisation is the parent atom or molecule M in the gaseous phase goes to M plus gas plus an electron. Now what we're doing is we're actually measuring the mass of the M plus ion, and we're assuming that the mass of an electron is very, very small. So we're assuming that the mass of the M plus ion is the same as the parent molecule or compound. Now it also tells us on the next row that each ion is accelerated to a kinetic energy value of 1.36 times 10 to the minus 16 joules, and it also tells us the equation for kinetic energy, which is given by 1/2 mv squared. Now the kinetic energy is measured in joules, but here what's really important and a really common place for students to go wrong is that in this kinetic energy equation the mass is in kilograms. But in chemistry, we often work in grams, especially when we're talking about moles. So we often need to do a conversion in some point in these equations from kilograms to grams or from grams to kilograms. It tells us the units of speed in meters per second. And then in the question, it's given us the data for the length of the flight tube and then the time taken. The question actually wants us to determine the mass in grams. So yes, we will need to do a conversion of 1 mole of Y, not 1 ion, not 1 molecule, 1 mole of Y. And it's actually given us the Avogadro constant, 6.022 times 10 to the 23 as well here. And on the AQA spec, they only give you that if you actually need to use it in the question. So we are going to have to use that later. So where do we even begin here? Let's start at the very beginning. So we have to remember from our GCSE physics that speed or velocity equals distance over time. This is an equation that students do commonly remember, and they have given us the distance in the question and they have given us the time taken. So we can straight away put this into our velocity equals distance over time, and we can do 0.75 divided by 2.48 times 10 to the minus 5, and that gives us a value for the velocity. Now we need to use that in our KE equals 1/2 mv squared equation. So we then have KE equals 1/2 mv squared. So if we rearrange that for M, the mass, which is ultimately what we're interested in, we get M equals 2 KE over V squared. Now we know the kinetic energy from the question, 1.36 times 10 to the minus 16, and we've just worked out the velocity. We have to remember to multiply the kinetic energy by 2, and we have to remember to square the velocity, but we simply need to put these in our equation and then put it in our calculator, and we end up with our mass, but remember this mass is in kilograms. And we end up with 2.974 times 10 to the minus 25 kilograms. And usually in kilograms for these questions, we are looking at a scale of around times 10 to the minus 25. So if you remember that as well, you know you're sort of in the right ballpark figure. So what we now need to do is we want an answer in grams. So we're now going to convert that to grams. So we need to multiply that answer by 1,000, and that gives us 2.974 times 10 to the minus 22 grams. And again, in grams, that's usually the sort of correct ballpark figure, something times 10 to the minus 22. Okay, so now we have the mass in grams, but this mass in grams is the mass of the 1 ion that hit the detector in the mass spectrometer. And the questions asked us to work out the mass in grams of 1 mole. Now we know the mass of 1 ion. We also know that within 1 mole there will be 6.022 times 10 to the 23 of these ions. So to work out the mass in grams of 1 mole of Y, we can multiply the mass of one ion by the number of ions in 1 mole by Avogadro's number. So we can do 2.974 times 10 to the minus 22 multiplied by 6.022 times 10 to the power 23, and we end up with 179.1. And again, we give this to 1 decimal place because it is a relative formula mass. Now, in terms of marks for this, you would often get a mark for working out the velocity, a mark for the mass in kilograms, converting that to grams, and then a final mark for your answer as long as it's to 1 decimal place. So this is approximately a 4-mark exam question. So now it's your turn to try an exam style question. Again, if you pause this and have a go yourself, I'll go through the answer in a moment. I will just give you a hint that this is actually a 6-mark question rather than a 4-mark question. And at the very end of this question, you have to do 2 extra things. You have to state the mass number of the specific germanium ion and write down the species that hit the detector that was actually detected. So that's a little bit of a clue for you to think about. So if you pause your screen now, have a go at this on your own. I'll go through the answer in a second. Right, so hopefully you've had a chance to go through this on your own. So let's now have a look. We approach this in pretty much the same way as the one I did on the previous slide. So the first thing to do is to work out the velocity, and velocity is distance over time. And again, the distance is in centimetres this time though, and we need to convert that to metres, and the time is in seconds here. So we're going to convert centimetres to metres, 0.96, and divide it by the time, 4.654 times 10 to the minus 6 seconds, and that gives us a velocity of this value here. Now again, we've got our equation ke equals half mv squared. That was provided in the question for us, and we need to rearrange this for the mass. And again here, mass equals 2 ke over v squared. They've given us the kinetic energy, and we've just worked out the velocity. So we can put those in our equation, and we end up with the mass being 1.146 times 10 to the minus 25 kilograms. But remember that this was in kilograms, and we want our answer in grams. So again, we're going to times by 1,000, and we end up with 1.146 times 10 to the minus 22 grams. Okay, so that is the mass of one ion. And they've given us Avogadro's number. So we need to use that in the question. So we want the mass of 1 mole of ions. And this time we're going to take the mass of one ion, multiply it by the number of ions in 1 mole by Avogadro's number, and we end up with a value of 69.01. Now, if we were quoting this as a relative atomic mass, we'd go to 1 decimal place, but I'm just showing it you to 2 decimal places to show the rounding. Now, the question here has asked for the mass number of this germanium ion and to write down the species that was detected. Now, because this is 1 isotope of germanium, we actually give this to no decimal places. That's only if we're averaging all of the masses of all of the individual isotopes. So in this case, my mass number is 69. And my species detected is 69 germanium plus ion. Remember, it says species, that could be an atom, a molecule, a compound, or an ion. And remember, the thing that hits the detector is actually the positive ion. So we need that little plus bit on the end of our 69 germanium to get the mark here. This is 6 marks, 1 for the velocity, the 2nd mark for the mass in kilograms, the 3rd mark to the conversion to grams, then the overall mass, then the mass number, and then the actual species with the positive charge on the end. And that's the end of this lesson. Thank you very much for listening. And remember, if you enjoyed this video and found it useful, please like and subscribe. It's absolutely free for you to do, and it will help more than you realise. I can make more videos like this in the future. Also follow me on social media. On Instagram, I do really short snippets of revision, and also visit my website.